Everything you have been told about what happens at the center of a black hole is probably wrong. Not a little wrong, but fundamentally wrong. Wrong in a way that reveals one of the deepest unresolved mysteries in physics. You have heard the phrase repeated in countless documentaries and articles and textbooks. The singularity, an infinitely dense point where all the mass concentrates, where the laws of physics break down, where space and time themselves cease to exist in any meaningful way. Dramatic, definitive. Sounds like scientists figured out what happens at the center of a black hole. They have not. What actually sits at a black hole's center remains one of the greatest unsolved problems in physics. And the honest answer is that we do not know. Singularity, as commonly used, describes not what we have discovered, but where our equations fail, a placeholder for ignorance dressed up in mathematical language, a boundary beyond which current theories cannot make reliable predictions. The black hole itself, that much is real. We have photographed them, detected their gravitational waves, watched stars orbit around something massive and invisible at our galaxy's center. The event horizon, that boundary beyond which nothing can escape, stands as a prediction of general relativity that has withstood every test thrown at it. The singularity, though, that supposed infinitely dense point at the center, is not a confirmed feature of reality, but a sign that general relativity, brilliant and successful as it is, reaches a limit where it stops being trustworthy. Physicists working on this problem will tell you plainly, when an equation gives you infinity as an answer, that is not nature telling you something about the universe. That is mathematics telling you your theory has failed. This video explores that failure and what might replace it. By the end, you will understand what a black hole actually is in modern physics, why the popular picture of a singularity misleads, what general relativity actually says versus what it fails to say, how physicists think the singularity problem might be resolved, and what the Event Horizon Telescope images tell us about these questions. If you find value in explorations like this, in taking time to understand the actual state of scientific knowledge rather than oversimplified stories, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Starting with the definition matters here because precision matters. A black hole, in modern physics, is a region of space-time where, once inside a particular boundary called the event horizon, all future-directed paths lead inward. Crossing the event horizon means every possible direction you could travel, including time itself, points deeper into the black hole. No path leads outward. Signals cannot escape to distant observers. General relativity tells us this, and this much stands well established. The event horizon is real in the sense that it is a robust prediction of Einstein's equations, and every observation we have made remains consistent with its existence. Notice what I did not mention. Nothing about what happens at the center. Nothing about infinite density. No claim that all the mass concentrates at a point. The honest statement differs from the popular one. What physicists call a singularity in modern general relativity discussions is not a physical object, not a place you could point to on a map and say, there it is. Instead, it is commonly formalized as geodesic incompleteness, a a technical way of saying that mathematical paths describing objects in free fall cannot be extended, even though the traveller's proper time, their personal experience of time, remains finite. Think about what that means. Falling into a black hole, according to general relativity, at some point your mathematical trajectory simply stops. Not because you hit something, not because some physical process the equations describe destroys you, but because the equations themselves can no longer tell you what happens next. The mathematics runs out of track. This is what physicists mean when they say general relativity breaks down at the singularity. The theory does not describe some exotic physical state at the centre, but admits it cannot describe what happens there at all. Let me put this differently. The popular phrase, an infinitely dense point, is what physicists call a heuristic, a simplified picture meant to give intuition rather than a precise description of what the theory actually says. Classical solutions, like the Schwarzschild metric, which describes the simplest kind of black hole, contain certain mathematical quantities called curvature invariants that diverge as you approach the centre. They go toward infinity, which signals that the classical equations have pushed beyond the regime where they can be trusted. Equations giving you infinity is not physics revealing something about nature, but mathematics telling you that you have reached the edge of your theory's validity. It resembles asking how many feet per second you travel when standing still, where the equation divides by 0. The infinity carries no physical meaning. Your equation was not designed for that situation. This is the key insight lost in popular presentations. The singularity is not a confirmed feature of black holes, but a confession that general relativity, powerful as it is, becomes unreliable in extreme conditions where quantum effects should matter. I remember when I first truly understood this distinction, and I had to sit with it for a while because it changed how I thought about everything I had read about black holes. The singularity is not like a prediction we can test and confirm. It is the opposite. It is the point where prediction fails. Understanding why general relativity breaks down at the centre helps clarify what we actually know. General relativity models spacetime as smooth and continuous, one of its fundamental assumptions. Spacetime curves in response to mass and energy, and that curvature is what we experience as gravity. The equations are differential equations, describing how things change smoothly from point to point. Near the centre of a classical black hole solution, curvature can grow without bound. The mathematics says it keeps increasing, approaching infinity. Here is the problem, though. When curvature becomes extreme enough, we enter a regime where quantum effects cannot be ignored. Other situations in physics show where classical theories fail. Classical electromagnetism says an electron orbiting an atomic nucleus should spiral inward and crash into the nucleus in a tiny fraction of a second. That prediction is wrong, because at atomic scales, quantum mechanics takes over, and the classical description fails. Something similar happens with gravity. General relativity is a classical theory, treating spacetime as a smooth continuum describable without reference to quantum mechanics. At extremely small scales and extremely high curvatures, though, we expect quantum effects to become dominant. the smooth continuum assumption likely fails. The centre of a black hole is precisely the kind of regime where quantum gravity effects should matter. With curvature so extreme and scales so small that treating spacetime as a smooth classical continuum almost certainly breaks down as an approximation. This is what the singularity really represents. Not a physical place of infinite density, but a warning sign that a classical theory has been pushed beyond its domain of validity. The Hawking-Penrose singularity theorems, developed in 1965 and 1970, formalized this understanding. Roger Penrose showed in 1965 that under certain broad conditions, gravitational collapse in general relativity generically leads to geodesic incompleteness. Stephen Hawking and Penrose together extended these results in 1970 to cover more general scenarios. What these theorems demonstrate is that under reasonable assumptions about matter content and space-time geometry, general relativity predicts paths through space-time that cannot be extended indefinitely. Somewhere along the way, the mathematics stops. This is widely interpreted not as proof that singularities physically exist, but as a sign of classical general relativity's incompleteness in extreme regimes. The theory reaches a limit where it cannot describe what happens next. Think of it this way. Using Newtonian gravity to calculate what happens when you compress matter beyond a certain point yields nonsensical results. That does not mean nature is nonsensical, but that Newton's theory does not apply in that regime. Einstein's general relativity replaced Newton's theory for extreme conditions like strong gravitational fields and high velocities. Similarly, we expect some quantum theory of gravity will replace general relativity in extreme conditions near what we currently call a singularity. The singularity theorems tell us where general relativity fails. They do not tell us what the correct description is. Let me take you through the history of how we got here, because the story reveals something important about how scientific understanding develops. Conceptual roots of black holes go back surprisingly far. 1783 brought an English natural philosopher named John Michell, imagining what would happen if you had a star massive enough that its escape velocity exceeded light speed. He called these hypothetical objects dark stars, bodies so gravitationally powerful that light itself could not escape. Michell worked within Newtonian physics, treating light as particles subject to gravity. The concept was incomplete, built on wrong assumptions about light's nature, but it planted the seed of an idea that gravity could be strong enough to trap light. 1687 had brought Isaac Newton's formalization of gravity as an inverse square force, a mathematical description working brilliantly for planetary orbits and everyday phenomena. Newton's framework treats space and time as fixed backgrounds, though, absolute stages on which physics plays out. This framework would eventually prove incomplete for extreme gravitational situations. 1915 brought Albert Einstein completing his general theory of relativity, a revolutionary reconceptualization of gravity, not as a force, but as space-time curvature caused by mass and energy. This was not just the modification of Newton's theory, but a fundamentally different picture of what gravity is. Einstein's equations allowed solutions describing scenarios Newton's physics could not properly handle. including solutions describing what happens when massive objects collapse under their own gravity. 1939 brought Robert Oppenheimer and Hartland Snyder publishing a paper analyzing gravitational collapse within general relativity. Their idealized model showed that under the right conditions, matter could collapse to form what we would now recognize as a black hole. The physics described an event horizon forming, a boundary beyond which nothing could escape. What about the interior, though? What happens to the collapsing matter? Classical equations suggested collapse continues beyond the event horizon, with matter falling inward. Describing what happens at the very end of that collapse proved problematic, though. The equations led toward infinite quantities, curvatures without bound, mathematical breakdown. For decades, physicists debated what these solutions meant. Some thought they were mathematical artifacts, peculiarities of idealized assumptions that would disappear in realistic scenarios. Others believed they pointed to genuine features of nature. The singularity theorems of the 1960s and 1970s changed this debate. Penrose's 1965 theorem and the subsequent Hawking-Penrose results of 1970 showed that mathematical breakdown was not a quirk of special cases. Under broad and physically reasonable assumptions, general relativity generically predicts geodesic incompleteness. The singularity problem was not going away. This was a turning point. The theorems did not prove singularities exist in nature. They proved that general relativity as a theory has this feature built into it. Trusting general relativity all the way down yields singularities. Here is the key question. Should we trust general relativity all the way down? Quantum mechanics' emergence in the early 20th century had already shown that classical theories, however successful in their domain, could fail at small scales. Classical electromagnetism fails for atoms. Classical statistical mechanics fails for low-temperature phenomena. The pattern was clear. Classical descriptions have limits. By the 1970s, physicists widely suspected general relativity too would prove incomplete at sufficiently small scales and extreme conditions. The singularity was not taken as prediction of what nature actually does, but as signal that we needed a quantum theory of gravity to describe those regimes. Between 1973 and 1975, the framework of black hole thermodynamics emerged, connecting black holes to concepts from thermodynamics and quantum mechanics. Discovery that black holes have entropy proportional to their horizon area, and Hawking's calculation that black holes should radiate quantum mechanically hinted that black holes had more structure than classical general relativity suggested. If black holes have entropy, they have microscopic degrees of freedom. If they radiate, quantum effects matter. The classical picture of a smooth interior leading to a singularity began to look incomplete. Let me explore the scale comparisons more deeply, because these numbers help convey how extraordinary these objects are, and how different our intuitions can be from reality. When I first calculated average density inside a supermassive black hole's horizon, I had to check my arithmetic 3 times, because the result seemed wrong. For a one solar mass black hole, average density inside the event horizon is approximately 1.84 times 10 to the 19th power kilograms per cubic meter. That is roughly 1.84 times 10 to the 16th grams per cubic centimetre. Nuclear matter has a density of about 10 to the 17th kilograms per cubic metre. So, a stellar mass black hole has average internal density comparable to or exceeding nuclear density. That makes intuitive sense. Something called a black hole, something associated with extreme gravitational compression, should be extraordinarily dense. Here is where intuition fails. M87 star, with its mass of 6.5 billion solar masses, has average density inside the event horizon of only about 0.44 kilograms per cubic metre, approximately 0.027 pounds per cubic foot. Air at sea level has density of about 1.2 kilograms per cubic metre. Average density inside M87 star's event horizon is less than half the density of the air you are breathing right now. The answer is the scaling. Schwarzschild radius scales linearly with mass, while volume scales as the cube of the radius. As mass increases, volume increases even faster. Average density equals mass divided by volume, so for larger black holes, average density actually decreases. This is a heuristic calculation, not a literal description of what the interior is like. General relativity does not say the interior is uniformly filled with something at that density. It illustrates how counterintuitive these objects are, though. You could, in principle, have a region of no return, a black hole event horizon, enclosing volume less dense on average than the air around you. The determining factor is not density, but mass and geometry. Event horizon forms when mass compresses below a certain radius, and for large masses, that radius is so large that average density ends up modest. This is one reason supermassive black holes have such gentle horizons. Tidal forces at the horizon depend on how rapidly gravitational conditions change over distance. For a large horizon, changes are more gradual. Before we explore what might replace the singularity, let me help. You picture black holes in concrete terms, because understanding the scales involved reveals something important. For a non-rotating black hole, described by the Schwarzschild solution, event horizon has specific radius, determined by mass. The formula is straightforward. Schwarzschild radius equals roughly 2.95 kilometers per solar mass, about 1.83 miles per solar mass. Let me make that concrete with examples. Compressing Earth's entire mass into a black hole would yield an event horizon with radius of approximately 8.87 millimeters, about 0.349 inches, smaller than a marble. All of Earth's mass, a sphere roughly 12,700 kilometers in diameter, squeezed into a region smaller than your fingertip. At the other extreme, consider Sagittarius A star, the supermassive black hole at our Milky Way's centre. With mass of about 4 million solar masses, its event horizon has radius of approximately 11.8 million kilometres, about 7.34 million miles. Substantial, roughly 17 times the Sun's radius. M87 star, the supermassive black hole imaged by the Event Horizon Telescope in 2019, is even larger. With mass estimated at 6.5 billion solar masses, give or take 0.7 billion, Its event horizon radius works out to approximately 19.2 billion kilometers, about 11.9 billion miles. That is roughly 128 astronomical units, meaning M87 star's event horizon extends about 128 times farther from its centre than Earth sits from the Sun. Think about that for a moment. A region of no return that would engulf most of our solar system. Here is something counterintuitive these numbers reveal. You might expect approaching a black hole would always be catastrophic, that gravitational forces would tear you apart long before reaching the event horizon. For small black holes, this is true. For supermassive black holes, it is not. The relevant quantity is tidal force, the difference in gravitational pull between two nearby points. Falling feet first toward a black hole, gravity pulls on your feet more strongly than your head because your feet are closer. This differential stretching would tear you apart, a process with the colourful name spaghettification. Tidal force at the event horizon depends on black hole mass, and it depends in a surprising way. Larger black holes have gentler horizons. For a 10 solar mass black hole, tidal acceleration across a 2-meter object at the event horizon is approximately 200 million meters per second squared. That is tens of millions of times Earth's surface gravity. You would be torn to atoms long before reaching the horizon. For Sagittarius A star, 4 million solar masses, tidal acceleration across that same 2-meter object at the event horizon is only about 0.0013 meters per second squared. Barely perceptible, far less than the gentle acceleration you feel in an elevator. This reveals something important. You could cross a supermassive black hole's event horizon without experiencing anything dramatic at that moment. The horizon is not a physical barrier, but a point of no return, and the crossing itself could be surprisingly gentle. What happens afterward is where the mystery begins. Let me discuss the relationship between the singularity problem and the information paradox, because these issues are connected, and both point to the need for quantum gravity. In classical general relativity, information falling into a black hole is lost forever. A book that falls past the event horizon cannot send any signal back. Eventually, if Hawking radiation is correct, the black hole evaporates. But the radiation appears thermal, carrying no information about what fell in. This creates a paradox. Quantum mechanics requires information preservation. If you know a system's quantum state at one time, you can, in principle, reconstruct it at any other time. Information cannot be destroyed. Black holes seem to destroy information, though. Whatever quantum state falls in, the same thermal radiation comes out. Detailed quantum information appears erased. For decades, physicists debated how to resolve this. Some, including Hawking for a time, believed information was genuinely lost, implying quantum mechanics needed modification. Others believed information was somehow preserved, even if we could not see how. Current consensus, though not unanimous, is that information is preserved. Various mechanisms have been proposed, including the holographic principle and the fuzzball proposal. How does this connect to the singularity? In the classical picture, information falls toward the singularity and is destroyed when it arrives. If the singularity is where physics ends, then information ending there is consistent with physics ending. If the singularity is not real, though, if quantum effects replace it, then information's endpoint is different. In loop quantum gravity models, information passing through the quantum region might emerge somewhere else. In the fuzzball picture, information never falls into an interior to begin with, but is absorbed into horizon-scale structure. Both approaches suggest the classical picture of information destruction is wrong, because it relies on the classical picture of the singularity, which is itself wrong. Fix the singularity problem, and you might fix the information problem. This is speculative. We do not have a complete solution to the information paradox. The connection between singularity and information problems suggests they are aspects of the same underlying issue, the need for a quantum description of black hole interiors. Let me also discuss what observations might someday tell us about these questions. Black hole interiors are directly unobservable. No signal can escape the event horizon to tell us what is inside. Any picture of the interior is theoretical extrapolation. Indirect evidence might help distinguish between theories, though. Gravitational waves from black hole mergers carry information about the merging black holes. If quantum corrections to general relativity are significant near the horizon or in the merger process, they might leave imprints on gravitational wave signals. So far, observations by LIGO and Virgo are consistent with classical general relativity, but future, more sensitive detectors might detect deviations. Hawking radiation, if we could ever detect it, might carry information about black hole internal structure. Astrophysical black holes have temperatures so low that Hawking radiation is undetectable, but spectrum and correlations in the radiation could, in principle, distinguish between theories. The cosmic microwave background might carry imprints of quantum gravity effects from the very early universe. If loop quantum cosmology is correct, there might be subtle signatures in the CMB from the quantum bounce that replaced the Big Bang singularity. Similar reasoning might apply to black holes formed in the early universe. High-energy particle collisions, if they ever reach energies near the Planck scale, might produce microscopic black holes whose properties could test quantum gravity predictions. This is far beyond current technology, but not impossible in principle. None of these observations is currently feasible at sensitivity needed to test quantum gravity predictions. They represent paths by which experiment might eventually constrain theory, though. In the meantime, theoretical consistency provides some constraints. A quantum theory of gravity must reproduce general relativity's successes in regimes we can test. It must be consistent with quantum mechanics. It should resolve the singularity problem and, ideally, the information paradox. Both loop quantum gravity and string theory aim to satisfy these criteria. Their different approaches lead to different pictures of what happens inside black holes. Eventually, experimental evidence should help distinguish them, even if that evidence is indirect. Let me explain the Hawking-Penrose singularity theorems in more accessible terms, because they are central to understanding why physicists take the singularity problem seriously. The theorems do not say anything about infinite density or points of zero size. They are stated in terms of geodesic incompleteness. A geodesic is the path an object in freefall follows through spacetime. In flat spacetime, geodesics are straight lines. In curved spacetime, geodesics curve in ways we perceive as gravitational motion. The Moon follows a geodesic around the Earth. A ball you throw follows a geodesic through Earth's slightly curved spacetime. A geodesic is called complete if it can be extended arbitrarily far in both directions, meaning the object following it exists for all time, past and future, as far as you want to extrapolate. A geodesic is incomplete if it terminates at a finite value of the affine parameter, which for massive particles corresponds to proper time. What the Hawking-Penrose theorems prove is that under certain conditions, geodesic incompleteness is unavoidable in general relativity. Some geodesics cannot be extended. They end. The conditions are broad and physically reasonable. They include assumptions about matter content, that it satisfies certain energy conditions, meaning it has positive energy density and does not exert excessive negative pressure. They include assumptions about geometry, that certain trapped surfaces form, regions from which light cannot escape outward. Under these conditions, the theorems say, general relativity predicts geodesic incompleteness. Paths through space-time simply end. What does ending mean? In the mathematical sense, the differential equations describing the geodesic cannot be extended further. There is no solution beyond a certain point. The mathematics stops. Physically, this is strange. We expect physics to tell us what happens next. If an object exists at one moment, physics should tell us what happens at the next moment, and the next, indefinitely. A theory saying the description just stops is either describing something genuinely terminal, like existence ending, for that object, or reaching limits of applicability. The Hawking-Penrose theorems do not tell us which interpretation is correct. They tell us geodesic incompleteness is a feature of general relativity. What we do with that information requires physical reasoning beyond the theorems themselves. Consensus interpretation is that geodesic incompleteness signals breakdown of general relativity, not actual end of physics. Just as the ultraviolet catastrophe signaled breakdown of classical physics for black body radiation, the singularity theorems signal breakdown of classical general relativity for extreme gravity. Think about what the alternative would be. If the singularity were real, if geodesics actually terminated, then objects falling into black holes would reach a point where existence simply stopped, not transformed into something else, not destroyed by physical processes, but simply ended. The mathematics would have nothing more to say about them. This is difficult to accept as description of physical reality. Physics describes transformations, processes, changes. It does not usually describe existence terminating without physical cause. Compare to other situations where physics describes destruction. A star can be destroyed by a supernova explosion. A particle can be destroyed in a high-energy collision. In both cases, though, there is physics describing the process. Energy and momentum are conserved. The destruction is a transformation, not a termination. The singularity, as classically described, is not like that. there is no physics describing what happens there because equations themselves break down. This is more plausibly interpreted as theory failing than as nature being fundamentally indescribable. This interpretation is strengthened by experience with other physical theories. When theories gave infinite or nonsensical results in the past, it usually meant we needed a better theory, not that nature was actually infinite or nonsensical. The ultraviolet catastrophe, where classical physics predicted heated objects should emit infinite energy at short wavelengths, was resolved by quantum mechanics. The infinity was artifact of using the wrong theory, not a feature of nature. The singularity is widely expected to have the same status. The infinity is artifact of using classical general relativity where quantum gravity is needed. Actual physics at what we call the singularity is quantum gravitational, not infinitely curved classical spacetime. To understand what might replace the singularity, we need to understand the scale at which quantum gravity effects are expected to dominate. This brings us to the Planck scale, a set of fundamental units where quantum mechanics and gravity both become important. Planck length is approximately 1.616 times 10 to the negative 35th power meters, about 5.30 times 10 to the negative 35th power feet. Distances so small they make an atomic nucleus look like a galaxy in comparison. Planck time is approximately 5.39 times 10 to the negative 44th power seconds, the time light would take to cross 1 Planck length. Planck mass is approximately 2.18 times 10 to the negative 8th power kilograms, about 4.80 times 10 to the negative 8th power pounds. Tiny by everyday standards, but enormous by particle physics standards, roughly the mass of a small piece of dust concentrated into a quantum scale process. At the Planck scale, quantum gravitational effects cannot be ignored. The smooth space-time general relativity assumes likely breaks down into something more fundamental, whether that is quantum fluctuations of geometry, discrete structures, or something not yet imagined. When physicists say the singularity should be replaced by quantum gravity effects, they mean that before conditions at a black hole's centre reach infinite curvature, they should reach Planck scale conditions, where classical description fails and quantum gravity takes over. What does quantum gravity actually predict? The honest answer is that we do not have a complete, experimentally verified theory of quantum gravity. What we have are several theoretical proposals, each suggesting different pictures of what might replace the singularity. Let me describe two of the most developed approaches. Loop quantum gravity begins from the premise that space-time itself should be quantized. Just as matter is made of discrete atoms, space-time might be made of discrete units at the Planck scale. In loop quantum gravity, fundamental variables are not the smooth metric of general relativity, but connections and loop-like structures. Quantizing these variables reveals that areas and volumes come in discrete quanta. Space is not continuous, but has grainy structure at scales of the Planck length. This discreteness has consequences for singularities. In classical general relativity, matter can be compressed to arbitrary density because space is continuous. In loop quantum gravity, there is minimum meaningful volume. You cannot compress matter indefinitely because space itself has a smallest scale. This does not mean there is a hard floor that matter bounces off. It means the concept of compressing to infinite density does not make sense in this framework. The question of what happens when matter reaches infinite density is as meaningless as what happens when you have negative apples. The framework does not allow infinite density. In practice, loop quantum gravity models of black holes typically show that as infalling matter approaches what would classically be the singularity, quantum effects become important. Curvature does not grow without bound, but reaches a maximum determined by Planck scale physics. And then something else happens. The 2018 work by Ashtekar, Olmedo and Singh provides one explicit example. They developed an effective description based on loop quantum gravity principles that extends the classical Schwarzschild and Kruskal geometries. In their model, singularity is replaced by a quantum transition region, what they call quantum transfiguration. In this picture, an infalling observer does not hit a singularity, but passes through a quantum region and emerges into a different part of extended spacetime. Geometry resembles the classical one outside the horizon, but is modified in the deep interior, with the singular point replaced by a quantum bridge. I want to be careful about this work's status. It is an effective model, an approximation based on loop quantum gravity principles, not a full solution in the complete theory. Loop quantum gravity itself remains a hypothesis, not experimentally confirmed. Even within loop quantum gravity, debates continue about correct treatment of black holes. What we can say is that in this approach, singularity resolution is natural. Discreteness of space prevents infinite compression. The classical singularity, always a sign of theory breakdown, is replaced by finite quantum physics. String theory takes a different approach. In string theory, fundamental objects are not point particles, but extended strings, tiny one-dimensional objects vibrating in various modes. Different vibrational modes correspond to different particles, with mass, charge, and other properties determined by how the string vibrates. Forming a black hole in string theory produces interesting results. The 1996 calculation by Strominger and Waffer was a breakthrough. They considered a particular type of black hole, a charged supersymmetric black hole in 5 dimensions, and showed you could count its quantum states using string theory techniques. The result was striking. Number of microstates matched the Bekenstein-Hawking entropy formula. String theory could explain why black holes have entropy, something classical general relativity could not do. If black holes have microstates, they have structure. They are not featureless geometric objects with nothing inside but empty space leading to a singularity, but are like any other quantum system with vast numbers of microscopic configurations corresponding to the same macroscopic state. The fuzzball proposal, developed by Mathur and collaborators in the 2000s, pushes this idea to its logical conclusion. If black hole entropy comes from string microstates, Maybe the entire black hole should be thought of as a string-theoretic object. In the fuzzball picture, what we call a black hole is actually a vast collection of string-theoretic configurations. From far away, it looks like a black hole with an event horizon. There is no classical interior, though, no empty space behind the horizon leading to a singularity. The whole interior is replaced by stringy structure extending throughout the horizon scale. This represents a radical departure from the classical picture. No interior means no singularity. The question of what happens at the centre does not apply, because there is no centre in the traditional sense. The fuzzball proposal remains controversial, even within string theory. Not all string theorists accept it. Alternative approaches suggest different pictures of black hole interiors. String theory itself remains unconfirmed experimentally. Let me discuss the historical development of how physicists' attitudes towards singularities have changed. In early days of general relativity, many physicists viewed singularity predictions with suspicion. Einstein himself was uncomfortable with them. The prevailing hope was that more realistic analyses, including matter properties and asymmetries, would show singularities were artifacts of idealized assumptions that would disappear in physical situations. Penrose's 1965 singularity theorem changed this. Penrose showed singularities were not artifacts of symmetric, idealized solutions. Under generic conditions involving trapped surfaces and energy conditions that should hold for normal matter, general relativity predicted geodesic incompleteness. The singularity problem was robust. The Hawking-Penrose extensions of 1970 broadened this result further, showing singularities appear in cosmological as well as black hole contexts under reasonable assumptions. These theorems shifted the conversation. The question was no longer whether general relativity predicts singularities. Clearly it does. The question became what to do about it. By the 1970s, with quantum mechanics well established and its conflict with general relativity increasingly apparent, prevailing view shifted to seeing singularities as signs of theoretical incompleteness. Just as the ultraviolet catastrophe signalled that classical physics could not describe black body radiation, the singularity problem signalled that classical general relativity could not describe extreme gravity. This remains consensus view today. Singularities are taken seriously as mathematical features of general relativity that need explanation, but not as literal descriptions of physical reality. Consider what the phrase "laws of physics break down" actually means. This phrase is often used casually to describe what happens at a singularity, and it is misleading. Laws of physics do not break down in the sense that physics stops working. What breaks down is a particular mathematical description, the classical general relativistic one. Actual physical laws never break down. Reality does not have gaps where physics fails. What happens is that current mathematical models reach limits of applicability. Consider an analogy. Using Newtonian mechanics to describe electrons in an atom yields nonsensical results. Electrons should spiral into the nucleus in a tiny fraction of a second. We do not say physics broke down in the atom. We say Newtonian mechanics does not apply there. Quantum mechanics does. Similarly, when general relativity predicts infinite curvatures, we should not say physics breaks down. We should say general relativity does not apply there. Something else does, presumably quantum gravity. The difference in phrasing matters because physics breaking down sounds dramatic and final, while theory reaching its limits sounds like a solvable problem. The second framing is more accurate. Consider the relationship between black hole singularity and cosmological singularity problems. General relativity also predicts a singularity at the beginning of the universe, the Big Bang. Running expansion backward, the universe appears to emerge from a state of infinite density and zero volume. This prediction has the same status as black hole singularity, a sign that classical general relativity is being applied where it does not belong, not a literal description of what existed at the beginning of the universe. Both singularities share the feature of occurring at scales where quantum effects should be important. Both are expected to be replaced by quantum gravitational physics. In loop quantum gravity, cosmological singularity resolution has been studied extensively, with results suggesting a quantum bounce. The universe did not begin from a singularity, but emerged from a prior contracting phase through a quantum transition. This is called loop quantum cosmology. If similar methods apply to black holes, the parallel is instructive. Just as the Big Bang singularity might be replaced by a quantum bounce, the black hole singularity might be replaced by a quantum region where something different happens. These connections suggest understanding black hole interiors might help with understanding the very early universe and vice versa. The problems are related, and a quantum theory of gravity should solve both. Why does this question matter for the foundations of physics? Physics currently rests on two incompatible frameworks: quantum mechanics, which describes the small, and general relativity, which describes the large and gravitational. Both work excellently in their domains. Neither can be extended into the other's domain without difficulties. The singularity problem is one of the clearest places where this incompatibility matters. General relativity predicts conditions where quantum mechanics must be relevant, but we do not have a framework for combining them. Resolving this incompatibility, finding quantum gravity, would be one of the great achievements of physics. The singularity question is a signpost pointing toward that resolution. Let me also discuss the idea that gravity could be strong enough to trap light, which goes back surprisingly far. 1783 brought John Michell imagining what would happen if you had a star massive enough that its escape velocity exceeded light speed. Working within Newtonian physics, treating light as particles subject to gravity, Michell calculated that a star 500 times the Sun's radius with the same density would have escape velocity exceeding light speed. Light leaving such a star would be pulled back like a ball thrown upward. Michell called these hypothetical objects dark stars. The concept was interesting, but built on assumptions we now know to be wrong. Light is not a particle subject to Newtonian gravity in the way Michell imagined. Correct treatment required both special and general relativity, which would not come for another century. Within months of Einstein publishing General Relativity in 1915, Carl Schwarzschild found an exact solution describing spacetime around a spherically symmetric, non-rotating mass. This Schwarzschild solution remains the basic model for understanding non-rotating black holes. The Schwarzschild solution contained a peculiar feature. At a certain radius, now called the Schwarzschild radius, mathematical description became singular. Metric components blew up. For decades, physicists debated what this meant. Some thought it was a coordinate artifact, a peculiarity of how Schwarzschild chose to describe spacetime, not a physical feature. Others thought it indicated something genuinely strange. Over time, resolution became clear. The singularity at the Schwarzschild radius is indeed a coordinate artifact. You can choose different coordinates, like Eddington-Finkelstein or Kruskal-Sekaresh coordinates, that are well behaved there. The event horizon is a physical feature, but it is not where physics breaks down. The singularity at the centre is different, though. No coordinate transformation can remove it. Curvature invariants, quantities that are the same in all coordinate systems, diverge there. This is a genuine feature of the Schwarzschild solution, not an artifact of coordinate choice. The question remained, does this singularity represent physical reality, or does it represent theory being applied beyond its domain of validity? Oppenheimer-Snyder analysis of 1939 showed gravitational collapse in general relativity could lead to formation of what we now call a black hole. Their idealized model described dust, pressureless matter, collapsing under its own gravity. Matter fell through its Schwarzschild radius, forming an event horizon, and continued collapsing inward. At this point, Einstein was still alive and deeply uncomfortable with these implications. He and others hoped more realistic analyses, including pressure, rotation, and asymmetries, would prevent singularity formation. Penrose's 1965 singularity theorem dashed those hopes. Penrose showed that under generic conditions, conditions that should hold for realistic matter undergoing realistic collapse, geodesic incompleteness was unavoidable. The singularity problem was robust. This was a turning point. The theorem did not prove singularities exist in nature. It proved that if general relativity is correct all the way down, singularities are generic. The question shifted from, can we avoid singularities in general relativity, to, should we trust general relativity all the way down? By the 1970s, consensus was forming that the answer to the second question was no. General relativity is a classical theory that must be replaced by a quantum theory at sufficiently extreme conditions. The singularity is where general relativity signals its own breakdown, not where physics actually becomes singular. Black hole thermodynamics. Development in the 1970s reinforced this view. Jacob Bekenstein proposed in 1972 that black holes have entropy proportional to their horizon area. Stephen Hawking showed in 1974 that black holes should radiate thermally due to quantum effects near the horizon. If black holes have entropy, they have microscopic degrees of freedom. If they radiate, quantum effects matter. The classical picture of a smooth interior leading to a singularity could not be the whole story. What do actual observations tell us about these questions? 2019 brought the Event Horizon Telescope collaboration, releasing the first image of a black hole, specifically the supermassive black hole at the centre of galaxy M87, known as M87 star. This was a landmark achievement. The collaboration combined radio telescopes across the globe to create an Earth-sized virtual telescope capable of resolving details at angular scales of millionths of an arc-second. The resulting image showed a ring of bright emission surrounding a dark central region. The emission ring had diameter of 42 microarc seconds, plus or minus 3 microarc seconds. This measurement is consistent with a black hole shadow interpretation in general relativity. The dark central region corresponds to light that has crossed the event horizon and cannot escape, while the bright ring is emission from hot gas orbiting just outside. From the image and supporting analysis, the collaboration estimated central mass at 6.5 billion solar masses, with uncertainty of about 0.7 billion solar masses. 2022 brought the Event Horizon Telescope, releasing an image of Sagittarius A star, the supermassive black hole at our own Milky Way's centre. This provided another confirmation that objects matching black hole predictions exist at galactic centres. Here is what these observations tell us and what they do not tell us. They provide strong evidence for horizon-scale structure consistent with general relativity. Size of the bright emission ring, shape of the shadow, dynamics of surrounding material all match what general relativity predicts for a region where an event horizon exists. They do not tell us anything directly about what happens at the centre, though. The observations probe the region near and outside the event horizon, not the deep interior. Light from inside the event horizon cannot reach us, so we cannot image the centre, regardless of how good our telescopes become. This is a fundamental limitation. The singularity question lies behind an information barrier. Whatever happens at a black hole's centre, whether classical singularity, quantum region, fuzzball, or something entirely different, that information cannot escape to tell us the answer. What we can do is test whether external predictions of general relativity hold up, and so far they do remarkably well. Event Horizon Telescope results are consistent with a Kerr black hole, the general relativistic description of a rotating black hole with an event horizon. Consistency with general relativity in the exterior does not validate the classical singularity prediction in the interior, though. Exterior and interior are separate questions. We can test one without testing the other. This brings us to an important methodological point about how physics works. When a theory makes predictions in one regime that we can test, and those predictions succeed, that gives confidence in the theory for that regime. It does not automatically give confidence in predictions for regimes we cannot test. General relativity has been confirmed in countless experiments and observations. Gravitational waves, Mercury's precession, gravitational lensing, GPS satellites correcting for relativistic time dilation. These successes establish that general relativity excellently describes gravity in regimes we can probe. A black hole's center is not one of those regimes. We cannot probe it directly. We cannot send instruments there and get data back. The singularity prediction lives in a zone where the theory has not been and cannot be tested. This is why physicists are skeptical of the singularity as physical reality. Not because general relativity's mathematics is wrong, but because the mathematics is being applied beyond the domain where we have any reason to trust it. Direct observation of the interior is impossible. Light cannot escape from inside the event horizon, so no signal from the deep interior can reach us. What researchers look for instead are indirect signatures. Quantum corrections to black hole physics might show up in subtle ways. Modifications to gravitational waves emitted during black hole mergers. Deviations from classical predictions for Hawking radiation. Unexpected features in the microwave background from the early universe. To date, no such signatures have been observed. Gravitational wave detections by LIGO and Virgo are consistent with classical general relativity. Event horizon telescope images match classical predictions. The cosmic microwave background fits the standard cosmological model without obvious quantum gravity modifications. This is not discouraging, though. Quantum effects are expected to be small in these contexts. They would show up most dramatically in situations involving Planck scale curvatures, which we do not have access to observe directly. What this means practically is that the singularity question remains theoretically motivated, but experimentally inaccessible. We have strong theoretical reasons to believe the singularity is not real physics, but we cannot observationally determine what replaces it. This is the honest state of knowledge. It might be unsatisfying if you want definitive answers, but it reflects where physics actually stands. Let me go deeper into what loop quantum gravity and string theory proposals actually say, because understanding them helps appreciate both possibilities and uncertainties. Loop quantum gravity begins from the premise that space-time itself should be quantized. Just as matter is made of discrete atoms, space-time might be made of discrete units at the Planck scale. In loop quantum gravity, fundamental variables are not the smooth metric of general relativity, but connections and loop-like structures. Quantizing these variables reveals that areas and volumes come in discrete quanta. Space is not continuous, but has grainy structure at scales of the Planck length. This discreteness prevents infinite compression. In classical general relativity, matter can be compressed to arbitrary density because space is continuous. In loop quantum gravity, minimum meaningful volume exists. You cannot compress matter indefinitely because space itself has a smallest scale. This does not mean a hard floor exists that matter bounces off. It means the concept of compressing to infinite density does not make sense in this framework. The question of what happens when matter reaches infinite density is as meaningless as what happens when you have negative apples. The framework does not allow infinite density. In practice, loop quantum gravity models of black holes typically show that as infalling matter approaches what would classically be the singularity, quantum effects become important. Curvature does not grow without bound, but reaches a maximum determined by Planck scale physics, and then something else happens. The 2018 work by Ashtekar, Olmedo and Singh provides one explicit example. They developed an effective description based on loop quantum gravity principles extending classical Schwarzschild and Kruskal geometries. In their model, singularity is replaced by a quantum transition region, what they call quantum transfiguration. In this picture, infalling observers do not hit a singularity, but pass through a quantum region and emerge into a different part of extended space-time. Geometry resembles the classical one outside the horizon, but is modified in the deep interior, with the singular point replaced by a quantum bridge. I want to be careful about this work's status, though. It is an effective model, an approximation based on loop quantum gravity principles, not a full solution in the complete theory. Loop quantum gravity itself remains a hypothesis, not experimentally confirmed. Even within loop quantum gravity, debates continue about correct treatment of black holes. What we can say is that in this approach, singularity resolution is natural. Space discreteness prevents infinite compression. The classical singularity, always a sign of theory breakdown, is replaced by finite quantum physics. String theory takes a different approach entirely. In string theory, fundamental objects are not point particles, but extended strings, tiny one-dimensional objects vibrating in various modes. Different vibrational modes correspond to different particles, with mass, charge, and other properties determined by how the string vibrates. Forming a black hole in string theory produces interesting results. The 1996 calculation by Strominger and Waffer was a breakthrough. They considered a particular type of black hole, a charged, supersymmetric black hole in 5 dimensions, and showed you could count its quantum states using string theory techniques. The result was striking. Number of microstates matched the Bekenstein-Hawking entropy formula. String theory could explain why black holes have entropy, something classical general relativity could not do. If black holes have microstates, they have structure. They are not featureless geometric objects with nothing inside but empty space leading to a singularity, but are like any other quantum system, with vast numbers of microscopic configurations corresponding to the same macroscopic state. The fuzzball proposal, developed by Martow and collaborators in the 2000s, pushes this idea to its logical conclusion. If black hole entropy comes from string microstates, the entire black hole should be thought of as a string-theoretic object. In the fuzzball picture, what we call a black hole is actually a vast collection of string-theoretic configurations. From far away, it looks like a black hole with an event horizon. There is no classical interior, though, no empty space behind the horizon leading to a singularity. The whole interior is replaced by stringy structure extending throughout the horizon scale. This represents a radical departure from the classical picture. No interior means no singularity. The question of what happens at the centre does not apply, because there is no centre in the traditional sense. The fuzzball proposal remains controversial, even within string theory. Not all string theorists accept it. Alternative approaches suggest different pictures of black hole interiors. String theory itself remains unconfirmed experimentally. Neither program has produced experimentally testable predictions allowing us to distinguish them from each other, or from classical general relativity in regimes we can currently access. This is one frustration of quantum gravity research. Effects are expected to be important only at scales and energies far beyond experimental reach. What would it take to test these ideas? Direct observation of the interior is impossible. Light cannot escape from inside the event horizon, so no signal from the deep interior can reach us. What researchers look for instead are indirect signatures. Quantum corrections to black hole physics might show up in subtle ways. Modifications to gravitational waves emitted during black hole mergers. Deviations from classical predictions for Hawking radiation. Unexpected features in the microwave background from the early universe. To date, no such signatures have been observed. Gravitational wave detections by LIGO and Virgo are consistent with classical general relativity. Event Horizon Telescope images match classical predictions. The cosmic microwave background fits the standard cosmological model without obvious quantum gravity modifications. This is not discouraging, though. Quantum effects are expected to be small in these contexts. They would show up most dramatically in situations involving Planck-scale curvatures, which we do not have access to observe directly. What this means practically is that the singularity question remains theoretically motivated but experimentally inaccessible. We have strong theoretical reasons to believe the singularity is not real physics, but we cannot observationally determine what replaces it. This is the honest state of knowledge. It might be unsatisfying if you want definitive answers, but it reflects where physics actually stands. Does it matter, though? If we cannot observe a black hole's interior, does the question of what happens there have any physical significance? I think it does, for several reasons. First, the singularity problem connects to other fundamental questions. The same theoretical frameworks addressing black hole singularities address the initial singularity, the Big Bang. Understanding one might help with the other. Second, singularities existing in a theory is often a sign of deeper inconsistency. If general relativity predicts physical infinities that do not correspond to reality, that tells us the theory is incomplete. Understanding why it is incomplete and how to complete it advances our understanding of gravity as a whole. Third, even if we cannot observe a black hole's interior, black holes interact with the universe in ways that might carry subtle signatures of interior physics. Hawking radiation, if we could ever detect it, might contain information about internal structure. Gravitational wave signals from black hole mergers might carry tiny imprints of quantum corrections. These are speculative possibilities, but they illustrate why the singularity question matters beyond pure curiosity. It connects to the broader project of understanding gravity, quantum mechanics, and their interrelation. Let me pause and consider what all of this means from a broader perspective. The story of the singularity is, in many ways, a story about the limits of human knowledge and how we navigate those limits. For centuries, physics has progressed by developing theories that work well in certain regimes, using those theories to make predictions, and then discovering where those predictions fail. The failures are not setbacks, but opportunities, telling us where the next theory is needed. Newton's gravity works brilliantly for most situations we encounter, but fails for objects moving near light speed and in strong gravitational fields. That failure pointed toward general relativity. General relativity works brilliantly for gravitational phenomena across scales from solar system dynamics to cosmic expansion, but appears to fail in extreme conditions at black hole centers and at the very beginning of cosmic history. That failure points toward quantum gravity. We do not yet have quantum gravity in the same way we have general relativity or quantum mechanics. We have proposals, frameworks, approximations. Loop quantum gravity and string theory are the two most developed, but neither has been experimentally confirmed. Both are works in progress. What we can say with confidence is this: the singularity predicted by classical general relativity almost certainly does not represent actual physics, but represents where the classical theory fails and something else takes over. This might seem disappointing. We want to know what happens at a black hole center. We want a definitive picture. Instead, physics offers honest uncertainty. We know the classical answer is incomplete. We have ideas about what might replace it, but we do not yet know which, if any, of those ideas is correct. I find this honest uncertainty more compelling than false certainty. It reflects the actual state of knowledge. It shows physics as it really is, an ongoing investigation rather than a finished edifice. A thought experiment helps clarify why the singularity picture is problematic. Imagine falling into a supermassive black hole, one large enough that tidal forces at the horizon are negligible. You cross the event horizon without incident. According to classical general relativity, what happens next? In the classical picture, your infall continues. You are now in a region where all directions lead inward. No matter what you do, you approach the singularity, reaching it in finite time, as measured by your own clock. What does reaching the singularity mean in the classical mathematics? Arriving at a point of infinite curvature, infinite density, infinite tidal forces. Your world line, the mathematical description of your trajectory through space-time, simply ends. This is geodesic incompleteness. Your path through space-time cannot be extended further. Not because you hit something and stop, but because the mathematics provides no description of what happens next. From a physical standpoint, this is deeply unsatisfying. Physics normally tells us what happens next. Even when something is destroyed, physics describes the destruction. Falling into the sun, physics tells you exactly how heat and pressure tear you apart. The process might be complicated, but it is describable. The singularity offers no such description. It is not that something complicated happens, but that the mathematics stops. The theory says nothing about what comes next, because there is no next in the classical description. This is why physicists believe the singularity is not real physics, but a sign of theoretical breakdown. Actual physics should describe what happens. A mathematical infinity that terminates world lines without describing what happens is almost certainly an artifact of using the wrong theory for that regime. Now consider what loop quantum gravity or string theory suggests. In loop quantum gravity, as you approach what would classically be the singularity, quantum effects become important. Curvature does not grow infinitely. Instead, quantum geometry takes over. The smooth space-time assumption breaks down, and something different happens. In some models, this is described as a quantum bounce, where infalling matter reaches extreme but finite conditions and then transitions to something else. In the fuzzball picture, the very notion of an interior approaching a singularity is replaced. There is no empty space inside the horizon. The horizon itself is the boundary of extended stringy structure. You would not fall through empty space toward a point because there is no empty space to fall through. These are very different pictures, and we do not know which, if any, is correct. They share a crucial feature, though. They replace the singular terminus with physics. Something happens rather than nothing happening. Mathematical stoppage is replaced by actual process. This is what physicists expect a quantum theory of gravity to provide. A description that works even in extreme conditions, that tells us what happens where general relativity falls silent. Let me address some common misconceptions about black holes and singularities, because correcting these helps clarify what we actually know. Misconception 1. The singularity is where all the mass of the black hole is located. In the classical general relativistic picture, mass that formed the black hole did collapse toward the center. Characterizing the singularity as where the mass is located is misleading, though, for several reasons. In general relativity, mass energy is associated with space-time curvature. The whole interior region of a black hole is curved, and the mass does not sit at a specific point in the normal sense. If the singularity is not actually real physics, then asking where mass is located inside the black hole may not have a classical answer at all. In the fuzzball picture, mass is distributed throughout the horizon scale structure. There is no central point where mass sits. The question of where the mass is has a different answer than the classical picture suggests. Misconception 2. The singularity is a point in space. This is tricky because the mathematics is subtle. In the classical Schwarzschild solution, as you fall past the event horizon, the radial coordinate that was space-like outside becomes time-like inside. The singularity is not a place in space that you approach, but a moment in time that you cannot avoid. This is hard to visualize because our intuitions are not built for curved space-time. Characterizing the singularity as a point in space is misleading. It is a boundary of the classical space-time, a place where world lines end, not a location in the ordinary sense. Misconception 3. Time stops at the singularity. This comes from confusing different perspectives. From a distant observer's perspective, time appears to slow down near the event horizon. An object falling in appears to freeze at the horizon, never crossing it. This is a coordinate effect, though, an artifact of how the distant observer describes time. For the infalling observer, time proceeds normally. They cross the horizon in finite proper time, and in their classical picture, reach the singularity in finite proper time. The singularity is not where time stops. It is where the mathematical description of the infalling world line ends. In quantum gravity proposals, the world line would continue in some form, not end. Misconception 4. We know what the inside of a black hole looks like. We do not. Everything we observe about black holes comes from outside or near the event horizon. The interior is causally disconnected from us. Any picture of the interior, whether classical singularity, quantum region, or fuzzball, is theoretical extrapolation, not observation. This is important to keep in mind. When documentaries show visualizations of black hole interiors, these are artistic interpretations of theoretical models, not observations. We do not know what the interior looks like. A thought experiment falling into Sagittarius A star illuminates the distinction between horizon and singularity. Suppose you are approaching Sagittarius A star, the supermassive black hole at our galaxy's centre. With mass of about 4 million solar masses and Schwarzschild radius of approximately 11.8 million kilometres, about 7.34 million miles. Approaching, you would see gravitational lensing bending light from background stars around it. You would see accretion disk, if one is present, glowing with radiation from hot gas spiralling inward. You approach the event horizon. In the classical picture, there is no physical barrier there, no surface you bounce off or crash into. Event horizon is a mathematical boundary, the point of no return. Crossing it, every path leads inward. For Sagittarius A star, tidal forces at the horizon are about 0.0013 meters per second squared across a 2-meter object. Imperceptible. You would not feel passage across the horizon. Inside, things become strange. The radial direction, which was a direction in space outside, becomes time-like inside. Moving toward the center is not like moving toward a destination, but like moving forward in time. You cannot avoid the center any more than you can avoid tomorrow. In the classical picture, you have some time before reaching the singularity, perhaps several hours of proper time. During that time, you would see space-time curvature increasing, tidal forces growing, the universe outside appearing increasingly blue-shifted behind you and increasingly red-shifted ahead. Eventually, in the classical picture, tidal forces would become overwhelming, stretching and compressing you beyond survival, and then beyond stability of matter itself. Equations say you approach infinite tidal forces at the singularity. This is where I want to emphasize. That infinite tidal forces conclusion is where classical theory breaks down. Long before conditions become literally infinite, they should enter the regime where quantum gravity matters. The singularity is not a physical destination, but a mathematical artifact of pushing classical equations too far. Consider another thought experiment to illustrate the situation. Imagine falling into Sagittarius A star. You cross the horizon without incident. In the classical picture, you now have finite time before encountering the singularity, perhaps several hours of proper time. During those hours, you could look around. What would you see? In the classical picture, you would see space-time curving more and more extremely as you fell inward. Eventually, curvature would become so extreme that tidal forces would destroy you, and then destroy particles you were made of, approaching infinite values at the singularity. In the loop quantum gravity picture, something different happens. Before conditions become infinite, quantum effects take over. Curvature saturates at some maximum value. What happens to you is still extreme, but it is physics rather than mathematics ending. Perhaps a quantum bounce, perhaps a transition to something else. In the fuzzball picture, there is no falling toward a singularity, because there is no empty interior to fall through. The horizon itself is the boundary of stringy structure. What happens as you approach is unclear, but it is not an empty fall toward a point. We do not know which picture is correct. We may never know through direct observation. We can say, though, that the classical picture, with its infinity approaching singularity, is almost certainly not the right answer. Let me offer perspective on scale once more, because understanding scale helps convey what is strange about these objects. Observable universe contains approximately 100 billion galaxies. Many contain supermassive black holes at their centers. Our Milky Way has Sagittarius A star, with 4 million solar masses. M87 has M87 star, with 6.5 billion solar masses. Other galaxies have black holes ranging from millions to tens of billions of solar masses. Every one of these black holes poses the singularity question. What happens at their centers? In the classical picture, each contains a singularity. In the quantum gravity picture, each contains something finite but unknown. Number of stellar mass black holes is even larger. The Milky Way alone might contain hundreds of millions of black holes formed from collapsed massive stars. The observable universe might contain countless trillions. Each is a place where current understanding runs out. Each is a question mark in the cosmic landscape, a region where general relativity admits its limitations and quantum gravity should take over. Looking at the night sky, you are looking at a universe filled with mysteries, concentrated in these dense, horizon-bounded regions. Mysteries we have characterized mathematically, mysteries we have begun to address theoretically, but mysteries not yet solved. The progression from mystery to understanding is the story of physics. A century ago, the nature of the atom was mysterious. Now we understand it in exquisite detail. 50 years ago, of quarks was mysterious. Now we have a standard model that describes them precisely. The nature of black hole interiors is mysterious today. A century from now, our descendants might have that mystery resolved, might look back at our uncertainty the way we look back at pre-quantum confusion about atoms. Or the mystery might prove harder, requiring conceptual revolutions we cannot yet imagine. Quantum gravity might be more difficult than quantum mechanics, requiring new mathematical frameworks, new physical intuitions, new ways of thinking about space and time. Either way, honest acknowledgement of current uncertainty is not failure of science, but its proper operation. Science advances by recognizing what we do not know, formulating questions precisely, and seeking answers through theory and experiment. The singularity question is at an early stage of this process. The question is formulated, candidates for answers exist, but experimental confirmation is far off. Living with uncertainty is part of understanding physics as it actually is. The universe does not reveal its secrets on our timeline. It reveals them when we have developed tools, theoretical and experimental, to extract them. For quantum gravity, those tools are still being developed. What I hope you take from this exploration is not certainty, but clarity. Clarity about what we know. Black holes are real. The event horizon is well tested. Exterior physics matches general relativity beautifully. Clarity about what we do not know. The interior, replacement for the singularity, correct theory of quantum gravity. Clarity about status of popular claims. The singularity is not a confirmed feature of reality, but a sign of theoretical limitation. This distinction between established knowledge, plausible hypotheses, and unknown territory is what science offers. It is more nuanced than dramatic certainties of popular presentation, but it is more honest and ultimately more interesting. Let me summarize what we have established and what remains uncertain. Black holes are real. This is not controversial among physicists. We have gravitational wave detections from black hole mergers. We have images of accretion disk shadows around M87 star and Sagittarius A star. We have decades of observations of stars orbiting something massive and invisible at our galaxy's centre. The event horizon is a well-supported prediction of general relativity, confirmed by observations consistent with its existence to high precision. The Event Horizon Telescope measurement of M87 star, showing emission ring diameter of 42 micro-arcseconds, matching theoretical predictions, stands as strong evidence that horizons exist as described. The singularity is not a confirmed feature of reality. It is a mathematical prediction of general relativity, emerging when you apply the classical theory to regimes where it almost certainly fails. The Hawking-Penrose theorems show this prediction is generic in general relativity, but physicists widely interpret this as showing incompleteness of the classical theory, not as confirming singularities exist. Two major theoretical approaches suggest what might replace the singularity. Loop quantum gravity models describe a quantum region where singularities are naturally resolved, with the 2018 work on quantum transfiguration providing one explicit construction. String theory's fuzzball proposal suggests black hole interiors are replaced entirely by horizon-scale stringy structure, with no empty space leading to a central point. Neither approach has been experimentally confirmed. Both remain hypotheses within larger theoretical frameworks that themselves await experimental validation. The singularity question is theoretically motivated, but experimentally inaccessible. What can we say with confidence? The classical picture of an infinitely dense point at a black hole centre is almost certainly wrong. It represents general relativity being applied, where it does not belong. Not a discovery about what exists in nature. What should we believe? That actual physics at black hole centers involves quantum gravity in some form? Whether that looks like loop quantum gravity, string theory, or something else entirely? The singularity is a sign that classical general relativity has reached its limit, not a feature of the physical world. An analogy might help clarify the situation. Imagine you have a map of a coastline, a good map, accurate at scales you need for navigation. Zooming in far enough, eventually the map cannot show smaller features. The map does not end because the coastline ends. It ends because the map was not designed to resolve smaller scales. General relativity is like that map. It is extraordinarily accurate for phenomena it was designed to describe. Pushing it to extreme conditions, though, to Planck-scale curvatures and densities, you are zooming beyond its resolution. The singularity is not the coastline ending, it is the map ending. Reality continues, but in a form the map cannot represent. This is the modern understanding of singularities in physics, not as physical places of infinite density, but as boundaries of classical theories where quantum effects take over. The failure of the map is not a feature of the territory. I want to share why I find this perspective more satisfying than the dramatic popular picture. The popular picture says, black holes contain singularities, points of infinite density where physics breaks down. This sounds deep, but is actually confession of ignorance dressed as knowledge. The scientific picture says, black holes exist, general relativity describes them well outside and near the horizon, but the classical theory fails in the deep interior where quantum gravity should take over. We have proposals for what that quantum gravity might look like, but we do not yet know which, if any, is correct. The scientific picture is more honest. It distinguishes what we know from what we do not know. It does not claim false certainty about the interior. It acknowledges limits of current understanding while pointing toward future research. This is how science works at its best, making clear what is established, what is hypothesized, and what remains unknown. The singularity question sits in the territory of hypothesized and unknown, not established. Let me reflect on what we have covered and what it tells us about scientific understanding. We started with a counterintuitive claim. The singularity, that icon of black hole physics, is almost certainly not a feature of physical reality. I hope I have convinced you that this is the consensus view among physicists working on these questions, and that it rests on solid reasoning. The journey to this understanding took decades, from Einstein's field equations in 1915 to Schwarzschild's solution in 1916, to decades of confusion about what the singularity meant, to the Penrose and Hawking theorems in the 1960s and 1970s, to development of quantum gravity proposals in recent decades. Each step built on previous understanding, and each step revealed new questions. This is how physics progresses, not by answering all questions definitively, but by replacing vague mysteries with precise questions. The vague mystery was what happens at a black hole center. The precise question became, how do we formulate a quantum theory of gravity that describes extreme gravitational conditions without producing singularities. The precise question is better because it points toward answers. We know what would constitute an answer: a quantum theory of gravity matching general relativity in testable regimes, resolving the singularity and remaining internally consistent. We have candidate answers in loop quantum gravity and string theory. We have ways, in principle, to test these candidates. Whether the answer will come in our lifetimes is uncertain. Quantum gravity is notoriously difficult, both theoretically and experimentally. Progress is being made, though, and questions are clearer now than they were 50 years ago. I want to leave you with a sense of where black hole physics stands as an active area of research. The Event Horizon Telescope continues to observe black holes and refine its techniques. Future observations might detect subtle deviations from classical predictions, though so far everything matches general relativity well. Gravitational wave astronomy is still young. LIGO and Virgo have detected dozens of black hole mergers. Future detectors, more sensitive and with different frequency ranges, will observe more mergers and probe them more precisely. Any quantum corrections to merger dynamics might show up in these observations. Theoretical work continues on both loop quantum gravity and string theory approaches to black holes. New models are being developed, consistency checks are being performed, and predictions are being refined. The hope is that at least some of these predictions will become testable. The information paradox continues to stimulate new ideas. Recent work on island contributions to entropy calculations has renewed interest in how information escapes from black holes. These developments might eventually connect to singularity resolution. We are not at the end of understanding black holes, but somewhere in the middle. With good knowledge of the exterior and horizon, deep uncertainty about the interior, and active research on all fronts. This is what makes physics exciting. Not finished answers, but ongoing investigation. The singularity question is part of the larger quest to understand gravity and quantum mechanics and their interrelation. That quest has been going on for nearly a century and will likely continue for decades more. When I contemplate black holes, I do not think of the misleading popular image of infinite density and physics breaking down. I think of objects we have photographed and detected, whose exterior physics we understand beautifully, whose interior physics remains mysterious, and whose mystery points toward deeper understanding not yet achieved. That is a more honest and ultimately more interesting picture. The mystery is not that nature contains infinities and breaks physics. The mystery is what actual physics operates in the most extreme conditions we can imagine. The answer, when we find it, will teach us something fundamental about how the universe works. Let me put the scale numbers in perspective one more time, because they help convey just how strange black holes are. Schwarzschild radius scaling of 2.95 kilometers per solar mass means a black hole's event horizon is proportional to its mass. Double the mass, double the horizon radius. This simple scaling leads to remarkable consequences. For stellar mass black holes, ones formed from collapsing stars with masses ranging from perhaps 5 to several tens of solar masses, the event horizon is remarkably compact. A 10 solar mass black hole has a Schwarzschild radius of about 29.5 kilometers, roughly 18.3 miles. An object with 10 times the Sun's mass, compressed into a sphere smaller than a city. For supermassive black holes, the numbers become cosmic. Sagittarius A star, at 4 million solar masses, has a Schwarzschild radius of about 11.8 million kilometers, roughly 0.08 astronomical units, about 1/20th the distance from Earth to the Sun. M87 star, at 6.5 billion solar masses, has a Schwarzschild radius of about 19.2 billion kilometers, or 128 astronomical units. The boundary of no return for M87 star extends well past Pluto's orbit, which averages about 40 astronomical units from the Sun. Think about that scale, an invisible boundary beyond which nothing can escape, larger than our entire solar system out to and past Pluto's orbit. All that space, all that volume, containing we know not what. Tidal force numbers tell an equally surprising story. For a 10 solar mass black hole, tidal acceleration across a 2-meter object at the horizon is about 200 million meters per second squared, roughly 20 million times Earth's surface gravity. The differential pull between your feet and head would tear you apart long before reaching the horizon. For Sagittarius A star, the same calculation gives 0.0013 meters per second squared, about 1/10,000th of Earth's surface gravity, barely detectable. You could cross that horizon without feeling anything unusual at the moment of crossing. This counterintuitive result follows from the mathematics. Tidal forces scale inversely with the square of distance from the centre. Since horizon radius grows linearly with mass, larger black holes have more gentle horizons. The implication is striking. Supermassive black holes. There is no violent death at the horizon. The horizon is not a physical barrier, but a point of no return, and the crossing itself could be anticlimactic. What comes after is where the physics we do not understand takes over. Let me put all of this in context of how physics has developed historically, because the pattern is instructive. Every major physical theory has had limited domain of validity. Newton's gravity works for everyday phenomena, but fails for extreme speeds and strong gravitational fields. Classical electromagnetism works for macroscopic phenomena, but fails for atoms and radiation. Statistical mechanics works for large systems, but needs modification for quantum systems at low temperatures. In each case, failure of the classical theory was not failure of physics, but a pointer toward new physics. The ultraviolet catastrophe did not mean nature was inconsistent, but that classical physics was incomplete. Instability of atoms in classical electromagnetism did not mean atoms could not exist, but that quantum mechanics was needed. The singularity problem has the same character. It is not failure of nature, but limitation of theory. General relativity, like all classical theories, has domain of validity beyond which it should not be trusted. What defines that domain? Generally, quantum effects become important when characteristic action of a process is comparable to Planck's constant, or when characteristic scales approach Planck length, time, or mass. At a black hole's centre, both criteria are satisfied. Curvatures approach Planck scale, and actions become small enough for quantum effects to dominate. The pattern from physics history is clear. When a theory gives infinities or nonsensical predictions, we should not accept those predictions as truth about nature, but recognize them as signs of theoretical incompleteness. This is not recent insight. Physicists recognized by the 1970s that the singularity was probably a sign of general relativity's incompleteness. What has taken longer is developing quantum gravity proposals concrete enough to say what might replace the singularity. That development is still ongoing. Loop quantum gravity and string theory both emerged in the late 20th century and have been refined since. Neither has achieved status of established physics. Both offer pictures of what might replace the singularity, but these remain hypotheses. The honest state of knowledge is that we know the singularity is likely not real physics. We have ideas about what might replace it, and we do not yet know which ideas are correct. Physics is about understanding how nature works. A puzzle like the singularity, where our best theory predicts nonsense, tells us there is something we do not understand. Resolving it would mean understanding gravity in extreme conditions, understanding the interface between gravity and quantum mechanics, understanding phenomena previously incomprehensible. This has practical implications, though admittedly long-term ones. Quantum mechanics, which resolved classical paradoxes, eventually enabled transistors and lasers and technologies that seemed like magic when quantum mechanics was first developed. Quantum gravity, if we understand it, might enable things we cannot currently imagine. More immediately, understanding quantum gravity would resolve foundational puzzles that have bothered physicists for decades. The singularity problem, the information paradox, initial conditions of the universe, all might become comprehensible. That is intellectually significant, even if it does not immediately lead to applications. There is also the simple value of accurate understanding. The popular picture of black holes with singularities of infinite density where physics breaks down is misleading. It describes our equation's failure as if it were nature's feature. Correcting this misconception brings understanding closer to what physicists actually believe. I think this matters even for non-physicists. We navigate the world partly based on understanding of how it works. A mistaken picture of black holes is a small error, but it is part of a larger pattern of confusing theory breakdown with nature's properties. Clarifying this distinction helps understand how science works. Science does not deliver final absolute truths. It delivers our best current understanding, which has limits. Recognizing those limits is part of understanding science properly. The singularity illustrates this vividly. A mathematical prediction almost certain in not representing physical reality. An infinity signalling theory failure rather than nature's infiniteness. Let me bring this exploration to a close by reflecting on what we have learned and what remains unknown. We started with a claim that might have seemed surprising. The singularity, the infinitely dense point at a black hole centre you have heard about countless times, is almost certainly not a feature of physical reality. I hope I have convinced you why physicists believe this. The singularity is a prediction of general relativity, but a prediction emerging from applying the theory to conditions where it should not be trusted. General relativity assumes smooth spacetime, but at Planck scale conditions that assumption fails. The singularity is not nature telling us something about infinite density, but mathematics telling us the theory has reached its limits. The analogy that stays with me is the map and the coastline. The map ends not because the coastline ends, but because the map was not designed for that resolution. The singularity is where the map of general relativity ends. Reality continues, but in a form the classical map cannot represent. What does continue there? We have proposals. Loop quantum gravity suggests a quantum region where space-time itself is discrete and singularities are naturally resolved. String theory's fuzzball picture suggests the entire black hole interior is replaced by horizon-scale stringy structure. Both proposals eliminate the singularity, replacing it with physics rather than mathematical breakdown. Neither proposal has been experimentally confirmed. The singularity question remains in the territory of theoretical physics, not established fact. This is honest uncertainty, the kind that drives research forward. The black hole itself is real. We have photographed the shadow cast by M87 star, with its emission ring of 42 microarcseconds matching predictions for a 6.5 billion solar mass object. We have imaged Sagittarius A star at our galaxy's centre. We have detected gravitational waves from black hole mergers. The event horizon, the boundary of no return, exists as general relativity describes. The interior remains mysterious, though. No observation can tell us what happens past the event horizon, because no signal can escape to inform us. The interior is forever hidden behind an information barrier. This might seem frustrating. We want to know. We want definitive answers about what happens at the centre of these cosmic objects. I find the honest uncertainty more satisfying than false certainty. Physics is an ongoing investigation, not a finished catalogue. The singularity question marks the frontier, the place where current understanding ends and future discovery begins. Here is what I want you to take away from this exploration. When you hear that black holes contain singularities, infinitely dense points where physics breaks down, remember this is a simplified story. The actual situation is more nuanced and more interesting. Black holes are real. The event horizon is a well-tested prediction. Exterior physics is understood and confirmed. The interior is unknown. The singularity is a mathematical artifact, a sign that classical general relativity fails rather than a description of what exists. Quantum gravity, in whatever form it takes, should replace the singularity with something finite and physical. We do not yet know what that something is. Loop quantum gravity, string theory, and other approaches offer possibilities. Future research might tell us which, if any, is correct. This is the actual state of scientific knowledge. It is incomplete but honest. It distinguishes what we know from what we theorize, from what we do not know at all. That is what I find beautiful about this subject. Not the dramatic but misleading story of infinite density and physics breaking down. The real story, of a classical theory reaching its limits and pointing towards something deeper not yet discovered. The next time you read about black hole singularities, remember this. The black hole is real, but the singularity, as commonly described, almost certainly is not. What actually exists at the centre remains one of the great open questions in physics. If you found this exploration worthwhile, if you value taking time to understand the actual state of scientific knowledge rather than simplified headlines, consider subscribing to the channel. It helps these deep dives reach more curious minds, and it tells me content like this resonates with you. Thank you for staying with me through this long journey. These questions deserve careful attention, and I appreciate you giving them that. Sleep well tonight, and maybe think about what lies at the center of all those black holes in the night sky above you. Not infinities and broken physics, but something real and physical that we have not yet discovered. The mystery is not that physics ends at the singularity. The mystery is what physics continues there, waiting to be understood. Good night.